Hey guys, as we continue looking at harmonic motion and waves, right, as we've transitioned into the part of the unit on waves, we're going to look at wave speed today. So wave speed, right, we can make modifications to our formula for velocity. If you remember way back, right, average velocity is your change in displacement over your time, right, delta x over delta t. But we can make a couple modifications to this formula to fit for what our velocity is for a wave. Because when you just watch a wave move, unless you send a single pulse, it's hard to get an idea of how fast the wave is actually moving, right? Because it's just going to go back and forth the entire time, right? If you get a wave and you just keep producing an identical pattern, it's going to just continue to move back and forth and back and forth and back and forth, and you can watch the wave and go, well, it's not going anywhere. Or I see it moving, but how can I define how fast it's actually going? So here's what we can do, right? We can make a little modification here, right? Instead of looking at delta x, we can look at our wavelength, right? So instead of what is the total distance that we've traveled, we can go, hey, how far has one wave gone, right? If we just define one wave, so one crest to crest, or one trough to trough, or even better, one full trough with one full crest, or vice versa, right? One crest with one trough. If we look at that wave, right, a single wave, and go, how far has that one wave moved, which would be the wavelength, that then gets rid of having to truly measure a delta x. And then in terms of our time, right, rather than looking at a total amount of time, well, how long did it take for that wave to oscillate back and forth, right? How long did it take for that wave to go crest to crest or trough to trough or one full crest and one full trough, right? What was the time period for that single wave? If we know the wavelength, right, how far, right, how far one wave traveled, which would be the wavelength, and if we know how long it took for that one wave to be completed, we have distance over time, right? Now it's just modified based on our terms that we're using now, right? Based on terms for waves. The way that this is properly written, it's actually in terms of frequency, right? So even though we can use lambda over the period, which is perfectly acceptable, the way that the wave speed equation is written is in terms of frequency, right? So we can pull lambda out and see that, hey, we have 1 over the period here. Well, we know that 1 over the period is the frequency, right? So the formula that we end up with is V equals F lambda, right? The frequency of that wave times the wavelength, right? That's what we have. And the beauty behind this is if we take a single wave and if you increase the frequency and the wavelength stays the same, the velocity goes up. If you keep the frequency the same and decrease the wavelength, the velocity goes down. More often what's going to happen though is as you change the frequency, you're going to see a change in wavelength, right? If you increase the frequency of a wave, typically that's associated with a decrease in the wavelength, thus causing the overall speed of the wave to stay the same. All right, that's why in the electromagnetic spectrum, for example, right, radio waves to gamma radiation, they all travel at the speed of light 3 times 10 to the 8th meters per second, right? They travel very, very, very fast, 300 million meters per second. But the frequency and the wavelength are what adjust there. Radio waves have really, really, really low frequencies, thus they have really, really, really high wavelengths. Wavelengths for the EM spectrum, they can range from kilometers down into nanometers. I mean, they can go from really big to really small. The frequency of the wave is what changes. So really, when you look at a wave, odds are its speed is going to stay the same. You're going to see an adjustment in frequency and wavelength is what we're going to have, right? So as frequency goes up, wavelength tends to go down. As wavelength goes up, frequency goes down. The velocity of that wave tends to stay put, especially if you're going through the same medium. So there we have it for our wave speed formula, right? Real quick example there on what we see, right? How we can modify it from basic mechanics, delta x over delta t, into our waves and how we perceive waves and how we look at waves in terms of wavelength and the frequency that that wave will oscillate.